Hello! In this video we are going to start learning how to write programs to test more complex propositions. You will have seen, perhaps, that the plan is that you should be able to write a computer program to test if a number is prime by the time you finish this batch of exercises. Without further ado then, let's get on to the content of this video. In the last few of these exercises, we have been investigating logical propositions and have been learning how to construct the negation of a proposition. In particular, we have seen that if we have a logical proposition A, the negation of A is a proposition that has a truth value of 0 whenever the truth value of A is 1, and a truth value of 1 whenever A has a truth value of 0. In the exercises, we have considered propositions such as A is less than B, A is equal to B, A is not equal to B, and so on. You are perhaps wondering what reason we have for introducing all this abstraction. The exercises, for instance, deal with relatively simple concept. It perhaps feels as if the abstraction in the explanations I have provided is just confusing matters. The answer to this is that a part of mathematics involves formalizing the way we think about the world. We use this formality when we explain simple ideas that it is likely students already understand and are able to manipulate without recourse to any of these abstract ideas. The hope is that when we then move on to discussing more difficult ideas, students are at least familiar with the tools that we are using. You can read more about what maths education is trying to do in this book, which I cannot recommend highly enough. If we return to the concept of propositions, for instance, while the propositions we have introduced thus far have all been things such as A is less than B, B is equal to 1, and so on, a proposition can be any statement with the form something, relation, something else. For example, the statement Dr. Trebello works at Queen's University, Belfast is a proposition. Similarly, SOR1020 is a course on probability and statistics is a proposition. Belfast is in Northern Ireland is a proposition, and so on. Furthermore, we can negate all these propositions. The negation of Dr. Trebello works at Queen's is Dr. Trebello does not work at Queen's. Similarly, the negation of SOR1020 is a course on probability and statistics is SOR1020 is not a course on probability and statistics. And lastly, the negation of Belfast is in Northern Ireland is Belfast is not in Northern Ireland. Now, none of the propositions we have constructed by negating these original propositions are true, but that is beside the point. The process of negating a proposition is an exercise in logic and not an exercise in finding truth. Let's now consider another mathematical proposition, the proposition that the number 3 is a prime number. To make sense of this proposition and to determine its truth value, we need to know how prime numbers are defined. If we look up this definition, or better still remember it, we find that a natural number p is said to be prime if it is not equal to 1 and if its only divisors are 1 and p itself. Notice that even this definition is constructed from propositions. For example, there is a proposition here that p is not equal to 1, and a second proposition here that the only divisors of p are 1 and p. There is then a logical conjunction between these two propositions. In short, propositions and logic are everywhere once you start to look for them. You can thus already use these ideas. To get better at maths, you need to be more careful and more aware of the way you are using propositions and logic. There is a balance to be struck, however, as if you try to be too rigorous and to always take everything back to the most basic definitions, you will go crazy. With that in mind, let's continue considering the definitions of prime numbers. If we take the second proposition from this statement about how the only divisors of p are 1 and p, which is the tricky one, we can see how this can be broken down into three further propositions, namely 1 divides p divides p, and for all k not equal to 1 and k not equal to p in the set of natural numbers, k does not divide p. We will come back to the last of these statements in a moment. For now, though, just know that we can replace the word divides in these two propositions with a vertical line as shown here. Divides is thus like equals, less than, more than, not equals, and so on. In other words, the proposition 1 divides p and p divides p have a truth value of 1 or 0, just as the proposition A is greater than B has a truth value of 1 or 0. As with anything in maths, though, we need to use a proposition to define what it means when we state that A divides B. The particular definition we use is shown at the top of the slide. We say that the proposition A divides B is true if there exists a natural number C such that B equals C times A. If we want to express this idea symbolically, we might write the proposition shown here, which we read as B divided by A is in the set of natural numbers if and only if A divides B. Notice again that we have two propositions. B divided by A is in the set of natural numbers, and A divides B. We also have a binary operator, the biconditional, that relates them, which tells us that the truth value of the second proposition is always the same as the truth value of the first proposition. This is all well and good, but how can we code all this with Python? When we learned about how to construct the propositions in if statements, I only gave you the options equal, not equal, less than, greater than, less than or greater than or equal. No information was given how to construct a divides option, mostly because there is no option. All you have at your disposal in Python are equal, not equal, less than, greater than, less than or greater than or equal. How then do you construct this proposition with divides? The answer to this is that if you want to test if A divides B using Python, you have to think about how to rework these propositions into a form that Python understands. In this case, we can do this by noting that if A divides B, then B divided by A is equal to the floor of B over A. The floor of a number is the integer you get when you round down. The floor of 3.2 is thus 3, the floor of 4.8 is 4, and the floor of 103.5 is 103. To get the floor of a number, you just delete everything after the decimal point. Given that if A divides B, then B over A is a natural number, there is nothing after the decimal point of B over A. So B over A is equal to the floor of B over A. We can now rearrange the expression we wrote and write B minus A multiplied by the floor of B over A is 0 if A divides B, instead of B over A is equal to the floor of B over A. The quantity we have computed here, B minus A times the floor over B over A, is the remainder when we do the division. To see what I mean, suppose that b is 5 and a is 4 here. The floor of 5 over 4 is 1, so b minus a times the floor of b over a is 5 minus 4, which is 1, the remainder when we divide 5 by 4. I mention this because Python has a command for calculating remainders like this directly. b%a is the value of the remainder when we divide b by a. We can thus use this percent operator and the other material on this slide to construct a proposition that we can put in an if statement to determine if a divides b. With that in mind, let's return to the business of determining if a number is prime. Recall that we said that a number is prime if for all k not equal to 1 and k not equal to p that are in the set of natural numbers, k does not divide p. Further note that we just established on the previous slide that a divides b if and only if b minus a times the floor of b over a is 0. And we have just established that we can calculate b minus a times the floor of b over a by using the percent operator in Python. Now notice the following alternative statement of the proposition at the top of the slide. There exists no I between 1 and p for which I divides p. We construct this proposition by noting first of all that none of the natural numbers that are greater than p will divide p. Furthermore, it stands to reason that if all of the natural numbers other than 1 and p do not divide p, there is no I that is both less than p and more than 1 which divides p. The nice thing about this alternative proposition is that we know everything we need in order to write a Python program to test whether or not this proposition is true, as shown here. Notice how within this code we run a loop over all the natural numbers that are greater than 1 and less than p, as shown here. Within the loop, we are then testing whether the loop variable, which remember will range from 2 up to p minus 1, divides p using what we have learned about the operator that is represented using the percent sign in Python. Outside the loop, we have set the truth value of the proposition prime equal to 1. If none of the values that we test divide p, then prime will still equal 1 at the end of the program. If, however, any one of the values does divide p, prime will be set equal to 0 as the proposition that p is prime is false. To summarize then, what we have shown is that we could write Python programs to determine the truth values of more complicated propositions, such as p is prime, by thinking carefully about the definition of prime numbers that is shown at the top of this slide. The Python code that we would write to test the proposition that p is prime is shown here. In terms of completing the exercises, there are two important ideas to consider within this code. The first of these is how we can construct a truth value of a proposition that involves a statement such as for all or there exists by testing a simpler proposition multiple times within a loop. The second key idea is the percent operator in Python. As we have discussed, p%i here returns the remainder when p is divided by I. These are the two ideas that you will need to use in the exercises that follow. Good luck, and as always, please do ask if you are struggling.